Hey, college algebra kids. Today we're looking at logarithms part 2, looking at common logarithms. Notes out, and away we go. So what are common logarithms? Common logarithms are logarithms with a base 10. So normally we would have written those as log base 10 of x. Because it's a common logarithm, we're going to actually skip the 10 or ignore the 10 and write it as log of x. But note, log of x always refers back to log base 10 of x. Now, how can we use that? Before there were calculators, logarithms actually were a good way to evaluate big numbers. And that's why exponent or logarithms came into fashion. For example, given that log base 7 is equal to 0.8451, evaluate each logarithm. So what are we going to do with log base 7? Log of 7 million. Well, note that this turns into log of 7 times log of 1 million. And then because we are multiplying, we're using the rules from the last lesson, because we're multiplying the logarithms, we can actually add them. So this turns into, and I wrote that wrong. So we're going to call this log of 7 times 1 million. And that turns into log of, because there's multiplication in the argument, then we can add them to get log of 7 plus log of 10 million. And so log of 7, well, we know that one. Log of 7 is given to us up here. That's 0.8451. Plus, then what's log of 1 million? Remember, this is base 10. So log of base 10 of 1 million. Can't ever get enough zeros in there. So that's 10 to the x is equal to 10 to the what power? Well, there's 6 zeros, so that's 10 to the 6th. Therefore, that's x equals 6. So that's plus just good old 6. Therefore, our answer is 6.8451. So that's how they calculated big values back before there were calculators. Let's do the same thing here. Log of 0.0007. Well, this is log of 7 times 10 to the negative 4th, basically. And then because it's multiplication, we can add these. So this is log base 7 plus log base 10 of 10 to the negative 4th. Well, that's just an exponent. That's got to come out. Log of 10 to the 10 is 1. So we got log base 7, which is 0.8451. This is a minus 4. And that gets us negative 3.1549. Go ahead and pause the video and try checkpoint 1. So we have log base 5 equals 0.6990. We evaluate each logarithm. So we're going to call this log of 5 times 10,000. Another way to think of this is log of 5 times 10 to the 5th. Sorry, 4th power. Well, and that becomes log of 5 plus log base 10 of 10 to the 4. If you remember back from college algebra, we had a property that said if these are the same, the base and the argument are the same, then it's just the value of the exponent. Log base 5 is 0.6990 plus 4, which is 4.6990. Letter B, this turns into log of 5 times 10 to the negative 3rd. That turns into log of 5 plus log base 10 of 10 to the negative 3rd. Again, we had a property that said if the exponent and the argument and the base are the same, then it's just this value. Log base 5 we know is 0.6990 plus negative 3 is negative 2.301. Example 3, evaluate each expression. So this is log of 5 plus log of 2 to the third. Because this is multiply, we're going to use again the properties from our last lesson. If we're going to multiply the arguments, then we're going to add the logarithms. So this is log of 5 plus log of 2 to the third power. We also had a property that said if we have an argument to an exponent, that exponent comes out in front as a coefficient. So this is log of 5 plus 3 log of 2. And then we can put that on our calculator using the log function, and we get 1.6021. Letter B, here we are dividing. If we're dividing the arguments, then we're subtracting. So this is log of 19 squared minus log of 6. Again, our exponent rule, this comes back out to be a coefficient. So 2 log base 10 of 19 minus log of 6. Again, we can put that on our calculator, 1.0012. Go ahead and pause the video and try checkpoint 3. And here we go. This becomes log of 3. Because we're multiplying, we can add the log of the arguments. 5 cubed, because that's an exponent, it comes out front. Log base 3 plus 3 log base 5. And that becomes 2.5740. Letter B, because we're dividing, again, we're going to subtract. So this is log of 13 cubed minus log of 7. That's 3 log of 13 minus log of 7. Put that on your calculator, we get 2.4967. Our next rule is the change of base formula for logarithms. We need to know this for variable purposes. If a, b, and n are positive numbers and neither a nor b is 1, then the following equation is true. Log base a of n. If we want to change from base a to any other base, typically we're going to use base 10 because that's the easiest, but you can change to any base you want to, is the same as log base our new base with the argument on top over the log of our new base with the old base on the bottom. So let's look at using the change of base formula. Find the value of log base 9 to the 1043rd using the change of base formula. Again, this question was more appropriate before we had calculators that would do all of this. But again, it's important to know this because you could have variables that you would use this as well. So we're going to change log base 9 to 10 to the 43rd. And again, we're just going to use log base 10 because that's an easy one to use. So log base 10, and the argument goes on top, 1043, divided by log base 10. The old base then goes on the bottom as the new argument. You need to put that in your calculator, and you get 3.1630. Go ahead and pause the video and try checkpoint 5 on your own. So checkpoint 5, find the value of log base 8 of 172 using the change of base formula. So this turns into log base 10 of 172. So the argument will go on the top, and then log base 10 of 8. Again, I didn't need to write the 10s. I could have called this log of 172 over log of 8. Those are the same. But I'm trying to emphasize that I'm just using base 10 here. And we can put that on our calculator, and you get 2.4754. Example 7, let's look at solving more equations. So solve 6 to the 3x equals 81. Well, the problem with solving this, again, is the x is in the exponent position. We don't want it to be in the exponent position, so how do we get it out? Well, for that, we have to use a logarithm. So we're going to change back to logarithm form. The base goes to the argument, back to the exponent. So log base 6 of 81 is equal to 3x. And finally, then, to solve for x, we can divide both sides by 3. Also, if we wanted to, we could use our change of base formula. So this would be log of 81 over log of 6 equals 3x. So divide by 3 gives us log base 81 over 3. There's our divide by 3, log of 6. And when you plug that into your calculator, you should get 0.8175. Checkpoint 7, same thing. We're going to start by turning this back into a logarithm. So this is log base 5 of 73 is equal to 4x. Now, yes, you can use your calculator to change that into a decimal and divide by 4. That would work. We can also use our change of base formula. So log of 73 over log of 5 is equal to 4x, and then divide by 4. So log base 73 divided by 4, log base 5, and then x gets you 0.6665. Last thing we're going to look at is solve by graphing. And the way this works, we're going to basically set each one of these equal to a y. So y1 is equal to 5x minus 1. y2 is equal to 2x. And so you're going to graph these on your calculator. And so let's try this. So we want 5 to the exponent x minus 1. If you have an older style calculator, remember, you might have to use parentheses there. And then this is y to the, not 2x, 2x is the exponent. And let's graph and see what happens. So there you can see they intersect. So we're going to do second calc. And we want to intersect to see where they intersect. We're going to hit 3 times, go from curve to curve, and yes, yes. And then therefore, we want the x is our solution. So x is 1.7564. Checkpoint 8, go ahead and pause the video and try that as well. Again, when you graph this, you should get 2 kind of exponential graphs that one's going to cross the other. When you check that, you get 2.76. Homework for 11.5 is page 730. 6, 8, 12 through 16 evens, we'll do those together in class. 20 through 26 evens, 34 through 50 evens, 55 through 57 even, 57 all. Have a good day, Maroons.